Hello everyone, welcome to my channel. So numerical solving set of linear equations specially is the most frequently used numerical procedure when real world situations are modeled. So you know that numerical analysis, especially numerical modeling, is a very important topic in applied mathematics. And linear equations are the basis for mathematical models of economics, weather prediction, heat and mass transfers, statistical analysis, and other applications. Maybe in the current scenario, the COVID 19 modeled, the pandemic, the greatest pandemic on the earth. And the methods of ordinary or partial differential equations depend on them. So we'll talk about this topic today. So in this chapter, we shall be concerned with the numerical computations of the solution of a system of n linear equations in n unknowns x1, x2, xn of the form. This is the system of linear equations, n equations with n unknowns, n linear equations in n unknowns. So this can be written in the matrix form also. If the coefficients aij, if you take the coefficient matrix A as A11, A12, etc. This is the coefficient matrix. You can take the coefficient matrix. And X is the column matrix, X1, X2, Xn. And B is the requirement, another column matrix at the given numbers. So this equation can be written as Ax equal to B. So this is the system of n linear equations in n unknowns. Now, how to solve this system of linear equations? In your +2 level, you have learned a method of solving system of linear equations, maybe two methods. One is a matrix inversion method, another is the Kramers rule. So these are direct methods. So the methods of solution of linear algebraic system of equations, one, can be classified as direct and iterative methods. So direct methods produce the exact solution after a finite number of steps, disregarding the round of errors. In these methods, we can determine the total number of operations, addition, subtraction, division, multiplications. We can calculate the total number of operations. This number is called the operational count of the method. And the direct methods are Kramers rule, Gauss elimination method, etc. And number two, there are iterative methods. Iterative methods are based on the idea of successive approximations. We start with an initial approximation to the solution vector. So your unknown vector is x. Look at that. If you write in a matrix form, it will be Ax equal to B. A is the coefficient matrix, x is the requirement vector, and B is the constants, set of numbers, column vector. X is the unknowns, x1, x2, xn. That is the requirement. So your approximation to the solution vector x equal to x naught, and obtained a sequence of approximate vectors x naught, x1, xk, etc., which is in the limit as k tends to infinity converges to the exact solution of vector x. So this is iterative methods. So you have classified into two methods only, direct method and iterative methods. So direct methods are Kramers rule, Gauss elimination. Iterative methods are Gauss, Seidel, and etc. We'll discuss about that. Now I will talk in this lecture today Gauss elimination and Gauss-Jordan. So what is Gauss's elimination? We assume that the given system of equations 1 has a unique solution. That means the coefficient determinant must be not equal to 0, and proceed as follows. Let us write aij 1 equal to aij and bj1 equal to bj, where ij equal to 1 to n. Let a111, that is the coefficient of the first equation of the first element. If you take the principal diagonal, this is your a11. Okay, I'm talking about this a11. So a11 not equal to 0. Let us suppose that a11 not equal to 0. Multiply the first equation by mi1, that is equal to minus ai1 by a11. If it is not equal to 0, that means I'm using the elementary row operations, and add to the ith equation when x1 is eliminated from that equation. So let me give you more idea on that. This is a11 not equal to 0. If this is not equal to 0, I am dividing the first equation by a11 and multiplying the first equation by a21, the second coefficient of second equation, x1, the coefficient of x1, and try to eliminate this x1. So what you have to do? You have to do r2 minus r1. Okay, after the multiplication. So that is how multiply the first equation. Okay, let me give you. Suppose your first row is 2x plus 3y plus 6z equal to 5, right? And your second equation is 7x plus 5y minus z equal to 2. So you want to, if you want to eliminate 7, if you want to eliminate this term, then what you have to do? You have to do it like divide the whole thing. You have to do r2 minus 7 by 2 r1, right? This is the operation you have to take, because you are multiplying, you are dividing the first equation by 2 r1. This is r1, right? You are dividing the first equation by 2 because 2 is a non-zero, and you are multiplying the whole equation by 7, the first equation, and subtracting from second equation r2. So this will goes, coefficient of x will be 0, this will be eliminated, and the further the calculation will be uh, implemented on the other coefficients. Okay, this is how. Similarly, you have a third equation, you have to eliminate like that. If the coefficient of the third equation is 3, then it should be minus 3 by 2 or 3 r1. Okay, like this is how. So this is the thing, and add to the ith equation when x1 is eliminated from that equation, and I can be 2. So x can be eliminated from the second equation, x can be eliminated from the third equation, x can be eliminated from the nth equation, giving the following equivalent system of equations. Let me see. Let us show you. So this is the first equation I was talking about, and what you have done, you are dividing by a111, right? This is your multiplier. So what is your multiplier? Look at that, your multiplier is mi1. So for the first case, your multiplier is m111. Your multiplier is m11. Okay, and that will be equal to minus, and this will be a21. This is your multiplier for the first equation. If you apply this multiplier to the for the second equation, if you apply this multiplier to the second equation, x1 will be eliminated. Similarly, what is the multiplier for the third equation? Third equation, your multiplier will be m21, right? I equal to 2, sorry, it will be 21, because I runs for I, this is the second, for second one, this is for second, and this is for third, so it will 31. m31 will be minus a311 by a11 1. So this is the multiplier for the third equation, and fourth, fifth, and so on, and finally the nth equation, like this. Okay, So your all the equations x1 will be eliminated. Look at that, there is no x, there is no x1. I was talking about x1, so there is no x1, so x1 got eliminated. Okay, this is the process of Gauss elimination. So following equivalent system, you have the system this. Okay, look at that multiplier, and your these are the relations aij2. Aij2 can be calculated like this. These are the coefficients you can calculate, because this multiplier will be operated in the second term, third term, nth term. So you will get the calculations of a22, a2a, a23, like this, a2n, and also you can calculate b2, b3, bn. Okay, this is how you can calculate. So this is very important steps. Now once your x1 is eliminated and you got the second system of equations, again you have to do the same process. You want to eliminate x2 now, so you have to divide by a222, the first equation, and multiply by, you have to select the multiplier. So in the second system, assume that a222 not equal to 0. We note that the set of equations 2 except the first is a system of n minus 1 linear equations, right? Except the first. In the n minus 1 unknowns x2, x3, xn, and applying the above elimination procedure to this system, x2 is eliminated from the last n minus 2 equations of the given, giving the equivalent system. It will give you the second. Look at that, your x2 is eliminated and your multiplier is given by this. So your multiplier for the third one, I equal to 3, 4, etc. So third multiplier, that is a multiplier for the third equation, because you want to eliminate x2 in the third equation, fourth equation, and so on, not in the second. So this is the multiplier. Again, a333 can be calculated by this, and b2, b33, b43, bn3 can be calculated using this. So using the same process, same thing, I will explain with an example. Then continuing this process, we finally obtain the following equivalent system of equations at the n minus 1th step. So if you follow the same steps, so this is your first equation, this is your second equation. If you eliminate x2, then you will get third, x3, and so on, x4, and finally you will get this equation. So this is the final steps, n minus 1 step system of equations, where MIK, this is the general multiplier, you can get this general multiplier, and this is aijk plus 1, bjk plus 1. You can get these values. So you are applying the same process. Okay, so now you look at that, you can get the values of xn from the last equation by the back substitution. Xn equal to bnn by annn if annn not equal to 0, and substitute the value of xn in the previous equation. So you will go from down. In the previous equation you will get xn minus 1. Then in the third last equation, you will, if you substitute xn minus 1 and xn, you will get xn minus 2, and so on. Finally you will get x1. So you are doing the back substitution process. This is called back substitution, not the forward substitution. You are doing the back substitution. That means you will start from the last equation. So also one more information, the leading coefficients, that is a111, a222, those are non-zero. A333, ANNN, these are called pivots, which are non-zero by assumption, are known as pivots, and the corresponding equations are called pivotal equations. Okay, now the system of equations is such that the corresponding coefficient, you look at that, your coefficient matrix will be looks like this, just like a upper triangular matrix. Okay, is an upper triangular matrix, a matrix in which all the elements below the principal diagonal are 0. Okay, this is your upper triangular matrix. This is how your upper triangular matrix. Okay, so this is your upper triangular matrix, and det A, if you calculate the determinant, it is non-zero because all the coefficients, all the leading elements are non-zero. So this determinant is non-zero, so it has a unique solution. Now the upper triangular system can be easily solved by back substitution, as I explained. How will you get the pi values by the back substitution? For the last one, you will get, if you divide bnn by ann, you will get xn. In the second last step, if you substitute the value of xn, you will get xn minus 1. Then in the third last step, if you substitute xn minus 1 xn, you will get xn minus 2, and so on successively. You will get all the values of the unknown variables. So this is called back substitution. Okay, and this is the method of Gauss's elimination with pivotal. Now there are a few questions for that. Okay, let me show you an example by Gauss's elimination. After that, I will go to some cases. Let me show you the problems. Yeah, solve the system of linear equations by, this is the using Gauss elimination with partial pivoting. Okay, what is partial pivoting? Partial pivoting means, let me explain that one first. Okay, let me go to some questions first. When does the Gauss elimination method is described above fail? It fails when any of the pivots is 0. That means the leading coefficients are 0, or it is very small number as the elimination progresses. If it is very small or the pivot is 0, then that method fails. If a pivot is 0, then division by it gives overflow error, since division by 0 is not defined. If a pivot is a very small number, the division by it introduces large round of errors. It will introduce large round of errors, and the solution may contain large errors. Okay, so this is the reason, or this is the method where limitation of the method. Now pivoting procedure that we needed here. How to avoid computational errors in Gauss elimination? To avoid computational errors, we follow the procedure of partial pivoting. As we require partial, what is partial pivoting? In the first stage of elimination, the first column of the augmented matrix is search for the largest element in magnitude and brought as the first pivot by interchanging the first row of the augmented matrix. First equation with the row equation having the largest element in magnitude. So in the first, so that will bring it forward. So that is called partial pivoting. In the second stage of elimination, the second column is search for the largest element in magnitude and among the n minus 1 elements, leaving the first element, and this element is brought as the second pivot by interchanging the second row of the augmented matrix with the later row having the largest element in magnitude. So this procedure is continued until the upper triangular system is obtained. So you have 3 columns, suppose. In the first column, you have to search for the largest magnitude of x1. So that will be brought forward in the first position, because this is the first pivotal element. This process will be continued in the second and the third. So this is called partial pivoting. Therefore, partial pivoting is done after every stage of elimination. There is another procedure called the complete pivoting. What is complete pivoting? It is a procedure we search the entire matrix A in the augmented matrix for the largest element in magnitude and bring it as the first pivot. So for the complete pivoting, you have to search for the entire matrix A, and that should become in the first position, and that will be taken as the first pivot. This requires not only an interchange of the rows, but also the interchange of the positions of the variables. This will interchange the position of the variables. Maybe y coefficient is larger in magnitude. Maybe z coefficient is larger in magnitude. So that comes to be in the first position. So that will interchange not only rows, but also the columns, and maybe interchanging the position of the variables. Now, it is possible that the position of a variable is changed a number of times during this pivoting. We need to keep track of the positions of all the variables. Hence, the procedure is computationally expensive and is not used in any software. So, partial pivoting will be preferred. So, you can go through the columns. So, I will explain in the example, then that will be cleared by you. Okay, I will explain after the problem, the Gauss-Jordan. Let me go to the problem. Now in this problem, you see, this is the system of equations. So let me, so you see, you just consider the first column. You just consider the first column. So the coefficient out of the coefficients of x1, 10 is the largest in magnitude, right? So you have to bring third row in the position of the first row. So you have to interchange the first and third. So I will write, let me write, you just note down the equation. 1 10 minus 1 2 3 20 10. Okay, let me write here, let me start here. 1 10 minus 1 2 3 20 and 10 minus 1 2, and you have a augmented portion 3 7 4. This is the augmented matrix, right? Now I will do the operation r1 3. So 3 will comes in the position of r1, and r1 go to the position of 3. So let me add a page here. Yeah, so I will do that. So I will apply r1 to r3, and r3 goes to r1, right? Because 10 is numerically largest. Okay, so magnitude is greater. So 10 minus 1 2, and this is 4, and 2 3 27, that remains same, and 1 10 minus 1 3. Okay, clear? Now I will apply the elementary row operation in this case. So 10, I will divide the whole first row by 10 and multiply it by 2 and subtract it from equation 2. So I will apply that method. So let me write the method r2 minus r1, or you can do r1 by 5, right? Because that, okay, let me write that one. So this will be r1 times 2 over 5. Okay, that will be the operation for r2. So your 10 minus 1 2 4. So this, and for r3, let me apply for r3, r3 minus r1 by 10. Sorry, this will be 10. Sorry, this will be 10. Okay, so this is the operation, this is the usual elementary logic. My target is to eliminate these positions. My target is to eliminate this position of x1, this position of x1. So this will be 0, right? This will be 0, this will be 0. And if you apply, so I have calculated this, I'm writing, you can check that. This is 19.6, because I have the calculation with me. So 6.2, 10.1, and minus 1.2, and this augmented portion will be 2.6. Okay, this is how. Now this is for elimination of x1. Now my target is to eliminate x2, the coefficient of x2. So your numerically larger one is 10.1 again. So it will go to this position, right? In the second position, and so we'll have to interchange r2 and r3, right? So let me interchange r2 r3, right? R2 R3 interchange. So it will be, and the equation 1 remains same. Okay, so 0 10.1 minus 1.2 2.6, and this will come to the third position 3.2 19.6 6.2. Okay, clear? And now do the operation. This is the pivotal second pivots, right? 10.1, and the first pivot is 10. This is your pivot. So A111, and this is your A122, right? This is your 222. Okay, so this is the second pivotal. Okay, now let me apply, I will apply the method R3 minus 3.2 by 10.1 into R2. Okay, because you see, you have to divide the whole equation by 10.1 and this, and after that you will get 10 The first equation remains same. Okay, 10 minus 1 2 4 0 10.1 minus 1.2 2.6 0 0 19.980 and 5.376. This is how you can calculate. Okay, I have calculated. So look at that. From the last equation, from the last one, you can calculate x3. You can calculate x3 by the back substitution. This is called back substitution. So your x3 is, so look at that. This is your upper triangular matrix. Okay, this is your upper triangular matrix. Below the, okay, you can apply this. These are the three pivots. Okay, so you can calculate the x3 by back substitution. 5.376 by 19.980. You can calculate this. So after calculation, it will be nearly to 0.27. So you can substitute x3 and you can calculate x2 here. So your x2 will be 1 by 10.1 into 2.6 plus 1.2 x3. If you substitute x3, you will get this. Look at that, minus 1.2 transfer to that side. So 1.2 x3 and plus 2.6 divided by 10.1. So if you know x3 from the previous step, you can calculate x2. Now x2, x3 can be substituted in the first equation. This is the first pivotal equation, second pivotal equation, third pivotal equation. So this is how you can do the problems of Gauss elimination by partial pivoting. At every steps, you have to change the pivots, and it depends on the numerically larger magnitude. Okay, so this is the process of pivoting. Let me now go to the next second method, that is the Gauss-Jordan method. I have explained this complete pivoting, and so partial pivoting is better than the complete pivoting, because complete pivoting is more expensive than this one, because you need more calculations to do, and maybe the variables will interchange their positions. So Gauss-Jordan method. So the method is based on the idea of reducing of the given system of equations Ax is equal to B to a diagonal system of equations Ix equal to D, where I is the identity matrix, and using elementary row operations, using simple elementary row operations, just I have explained, we know that the solution of both the systems are identical. This reduced system gives the solution vector x. This reduction is equivalent to finding the solution as x equal to A inverse B. So most important application of Gauss-Jordan method is the finding the inverse of the matrix. So actually Gauss-Jordan method is nothing but you have to bring in the left hand side a identity matrix. That's it. This is the difference between the Gauss elimination and Gauss-Jordan. So in this case, after the eliminations are completed, so this is not upper triangular matrix. You have to, your target is to bring identity matrix. So all the elements should be 0 except the diagonal. So eliminations are completed. We obtain the augmented matrix. This matrix will be looks like this at the final stage. So you see you have xi equal to di, that is x3 equal to d3, x2 is equal to d2, x1 equal to d1. So this takes too many, this method is very expensive than the Gauss elimination method, because it needs much more steps to calculate the process. So the first step is same as the Gauss elimination method. That is, we make the elements below the first pivot as zeros using the elementary row transformations. From the second step onwards, we make the elements below and above the pivots as zeros. You have to make the zeros in the above of the pivots using the elementary row transformations. Lastly, we divide each row by its pivot so that the final augmented matrix is of the form 9. Partial pivoting can also be used in the solution. We may also make the pivot as 1 before performing the elimination. Okay, so this is how you can do with the Gauss-Jordan method. Now let us compare the two methods. The Gauss-Jordan method looks very elegant as the solution is obtained directly. You don't have to solve back substitution method, don't have to apply. However, it is computationally more expensive, that I have earlier explained, that Gauss elimination method. For large and the total number of divisions or multiplications for Gauss-Jordan method is almost 1 1.5 times the total number of divisions and multiplications required for Gauss elimination. That is a huge, because for large n, the total number of divisions and multiplications of Gauss-Jordan method is almost 1.5 times the total number of divisions by Gauss elimination. Hence, we do not normally use this method for the solution of the system of equations. The most important application of this method is to find the inverse of a non-singular matrix. That's it. So if nothing is mentioned in the question, you will go for Gauss elimination. That is the direct method and the best method. In the direct methods, it is the best, and you will get the solution. But avoid Gauss-Jordan because of these drawbacks. So this is the thing. I know already we have explained the problems on Gauss elimination. So I think we are complete here. So this is the lecture today. So I hope this lecture is useful to you. Please share my lecture to all your friends, relatives, and please subscribe my channel, and please post some comments in the YouTube videos. Thank you, all of you.